welcome. This is the continuation of the previous lecture, where we have shown a realistic MATLAB model, and then we have shown the image file of the simulation result as well as experimental result. In this lecture, we are going to show the step for data acquisition through oscilloscope using CSV file, and how can we plot, how can we plot both simulation and experimental result using a single graph, and then we want to see how much they are actually matching, and if it is expected there will be some deviation from experimental and simulation result, and we want to try to understand what may be going wrong and why the difference is coming. So, here we will be talking about post processing of oscilloscope data and the summary of step, and then we will show the method of validation of simulation and experimental data. So, first we need to understand need for post processing. So, one of the purpose of the need, we want to post process the experimental data, we want to match sometime the discrete time large signal model for validation. We also want to study the comparative transient performance both simulation and experimental result. This will help to fine tune our simulation model, so that it can more or less capture the hardware result. It may not be possible to exactly match, but how far we can match, so that once we can capture that in the model, then we may not need to do lot of iteration in the hardware. So, we can do the design process using our analytical model, we can check in the simulation before going to the experimental validation, and that we will be discussing in this week in the subsequent lecture. And we will also show some assessment between simulation and experimental result, whether the models are accurate or there is a need for scope for improvement. So, first we will show that step for capturing oscilloscope waveform as a .csv file. So, here I am showing the screenshot of the oscilloscope. Here you can see this is the pen drive, oscilloscope will have a USB drive, and this is the running waveform, where we are showing the output voltage waveform here and the inductor waveform here live, and this is the current probe, and this is our signal conditioning board, and this below is our FPGA kit, and this is our power stage board. And we are actually trying to take the result. Earlier we took the image file, but now we want to take the CSV file. So, you have to insert the USB file, then you have to select the menu option. That means, if you go to the previous, there is a menu option here, you can see there is a menu option here. So, you have to select the menu option. If you select the menu option, then click the menu save and recall. There you will get an option that what type of thing you want to say. So, assign to whether it is an image file. So, that means, when you option the menu, it will come the save screen image. Right now it is the screen image, but we want to take the data file rather than the image file. So, then you have to click here. If you click here, then when you click this option, particularly if you click this button, particularly this particular button, then you will get the option. So, here by default we are getting the image file, but we want to take the waveform. If it is image file, it will be, we can save it in .bmp file. Typically we take the data in BMP. Now, so we have to assign save to image. If it is image, then it will be saved as BMP file. Okay. Now, so this will save as an image. Now, we want to change from image, because image we have shown in the previous lecture, the image of the simulation result and the image of the experimental result, but now we want to take the data and plot in the single command. So, then we have to change to the waveform. When you change to waveform, then the extension file will be shown as .csv, that is like a Excel file, .data file. Then you get for the save. When you say save, that means, this is the button that you have to press. When you press save, it will show the status that it is saving. So, that means, the data is saved. When the data is saved, then you open this USB file, that means, you remove that USB pen drive and connect to your computer. Once you connect to your computer, then you will get a file name called .csv accordingly, and if you double click, this file will open in Excel sheet. So, there will be a lot of information. It will show the model name of the oscilloscope, then waveform, probe attenuation, all this information there, but this is where your actual waveform will start. This is where. So, the first I will say the first column, it will be the time vector. The second column will channel 2, because we are only showing 2 channel. channel 2 and channel 4. If you go, we are showing this is in channel 2 is the output voltage, it is in channel 2, and channel 4 you can see here, channel 4 is my inductor current. Okay. So, the channel 2 is my output voltage and channel 4 is the inductor current, and this is captured by the probe. So, that means this will show the original currents and voltage. So, this time series data start from here, that means start from here. Then when you have to read the data, that means you start from 21, skip to, or you can remove this, then you recall the file name is stored as tech 0005 all dot, okay, dot CSV. Now, this CSV file, we have discussed how to capture the workspace data in the MATLAB. So, if you remember that we have saved our waveform of the simulation result in a dot, in the workspace, and the workspace we saw it is a structure where we have the first vector, which column vector, which was time, then we got a data vector, and the first column data was current, depending upon which column you are using. So, here we have 3 vector. The first column vector, the column 1 is the time vector. The second column vector is a, this will link with your time, it is a time vector. The column 2 is linked with your output voltage, it is channel 2, and the column 3 is linked with your inductor current. Okay? That we know. Once you get, then you are ready to plot. So, we are plotting, the data will be by default in second, we can multiply in 1 10 to the power 3, so that we can show in millisecond, because we want to show the data in millisecond, that is why you are scaling the time and you are plotting the output voltage waveform. So, this will plot the experimental data and you have to hold and grid it. Then on this plot 1, then similarly we can do plot 2, which is the inductor current waveform. Now, we want to hold the data and we want to plot the simulation data. So, this is the experimental data, that means we are plotting the experimental data, output voltage, and here there will be load step up transient and there is a load step down transient, and the experimental data naturally there will be some noise, these are not deterministic signal. So, these are basically stochastic signal, while we will have some noise also. Then, and this noise, since you are using a digital storage oscilloscope, that is why the data will look like a quantized data. Next, actual experimental data, you will see as if it is starting with some negative value. So, we need to apply some time offset, so that you can start this waveform from 0. So, you have to shift the right side, so you have to add a time offset. This is the inductor current waveform, it also has a time offset that you have to consider, and this is the experimental plot we are showing in the MATLAB, because we have already accessed the data. Now, next step, we want to compare this experimental result with simulation result. So, first you plot oscilloscope waveform from the CSV file, which you have just discussed, then apply step by step load transient simulation in our MATLAB file, and you just apply step up transient. Okay, so, first we have to show the step up transient. So, we need to properly set the time offset, so that both transient step up should happen at the same time for both simulation and the experimental case. Then we will apply step down, we can show the step down separately, and we need to again consider the time offset, and this is the step up transient. So, this is a step up transient comparative study, where the red one is the simulation result and the green one is the experimental result. So, we will see the experimental result, the current ripple is slightly higher, that means whatever inductor we have considered in the simulation, that is little bit larger than the actual hardware, and this might happen because in actual hardware the inductor can slightly vary. In fact, if you increase the current, the inductor variation may be large, because if you take the data sheet of any inductor, if you go to the data sheet, the inductor value may be same, then it will start degrading, and this is with respect to the current, and this is the inductor value, because it all goes down to the flux. Because if you go to the flux will enter into nonlinear region, where what is the definition of inductance? It is a change in flux by the change in current. If this is the current axis, this is the flux axis, naturally as it enter into saturation region, the flux change will be less. So, value of the inductor will go down. So, at practical inductance, so there is a scope for actually further tuning our simulation inductor value by taking into account this inductor. So, I think we may reduce the inductor value little bit. Now, since we are using slightly larger inductor in our simulation, as a result we are getting a little bit sluggish transient response, step up transient using simulation compared to the hardware result. That means, there is a slight difference, their undershoot remains more or less same, but there is a slight deviation in the I would say the recovery time. And that means, if you go back to our simulation result, I would say the simulation inductance value we may have to increase maybe by 5% or 10%. We may have to reduce, we may have to reduce the inductor value in the simulation case study, so that we can match the current ripple of the measured inductor current. So, that means, we can play around with the data and we can fine tune our simulation parameter, so that we can match. Okay. Now, this is a step down transient, again you can see there is a deviation in the measured current ripple and the simulated current ripple. So, we can increase, we can actually change this simulation inductor current by slightly decreasing the inductor value. Again we are our simulated parameter experimental simulated low step up transient step down has a slightly higher recovery time or the settling time compared to the experimental result. So, they and we have discussed they may not match exactly. So, there is a source of deviation, and this may be attributed to many unmodeled dynamics, like we have not considered the parasitic of the inductor in the like a ESL effect in the capacitor. We have not considered the dead time effect in our simulation, that can also be captured. We have not considered the other trace parasitic, and also we have not rightly modeled the inductor, which we can model by slightly decreasing the inductor value. And I hope if we do that, we may come further closer to the hardware result, but it is almost impossible, I would say very difficult to exactly match. So, in summary, we have shown the technique for post processing of oscilloscope data, we have shown the summary of steps, and we have discussed the method for validating simulation and experimental result, and we have discussed some aspect of mismatch between simulation and experimental result, and we have also discussed there are some room for improvement, and this may be the motivating case, and this kind of validation and further upgrading the model will help us to design the converter suitably, and so that you can design in your simulation or analytical model, and you can plug in simply to the experimental result, so that you can meet the desired performance requirement. That is it for today. Thank you very much.